Hello friends. So today we are going to discuss the questions which are from year 1998, and there are total of 4 questions, or we can say there are 4 PYQs, and all those questions are from 1998. So in the first one we are given a uniform constant magnetic field B is directed at an angle 45 degree to the x-axis in the xy plane. PQRS is a rigid square wire frame carrying a steady current I0 with its center at origin O. At the time t is equal to t0, the frame is at rest in the position shown in the figure, with its sides parallel to x and y axis. Each side of the frame is of mass m and length capital L. So based on this description, we have 2 questions asked on it. In part A, it is said what is the magnitude of the torque acting on the frame due to the magnetic field. And the second case B, it is said that find the angle by which the frame rotates under the action of this torque in a short interval of time delta t and the axis about which this rotation occurs. Delta t is so short that any variation in the torque during this interval may be neglected. Given that moment of inertia of the frame about an axis through its center perpendicular to its frame is perpendicular to the plane is given as 4 by 3 ml square. So we have a figure. In this we have a figure. We have a, you can say, square plane, and that is given as PQRS. And this square there is a magnetic field B, and this magnetic field B is making an angle of 45 degree with the x-axis, and the current direction is also given, and the magnitude is our I0 that is flowing through this square. So first of all, we are going to find out the torque acting on the frame due to the magnetic field. So let us start with part A. Part A, we are going to find out torque. Torque tau about the center O. And to find out the torque, we are going to use, first of all, calculate the magnetic dipole moment. So we say magnetic dipole moment, that is of m, will be equal to I0 A, and we have a unit vector n, and A is the area of the square. So we have area of square which is represented as A and will be equal to L square, and our unit vector n, this represents a, you can say, direction and perpendicular to the plane of the loop. Direction perpendicular to the plane of loop. And for the sake of convenience, let us assume it is out of the paper. Out of paper, or we can say in z direction. Therefore, we can write our dipole moment, magnetic dipole moment, will be equal to I0 L square, and here we have now z unit vector, and we are given a magnetic field, and that magnetic field is making an angle of 45 degrees with x-axis. So we have our magnetic field, that is our B, and it is making, or we can say lies in xy plane at 45 degree to the x-axis. So we can divide into two components, and let me draw a rough approximate of it. So we have, this is x-axis and we have y-axis. So accordingly here we are going to have x unit vector, and here you're going to have y unit vector. Magnetic field is making an angle of 45 degree. This is our B. Making an angle of 45 degree. Therefore, along x-axis, we can write this as B cos of 45, and with x unit vector, and along y-axis we can write it as B sine of 45 and with y unit vector. So we can say our magnetic field B will be equal to B cos of 45 x unit vector plus B sine of 45, and here we have y unit vector. Cos in sine 45 is 1 by root 2. So we can write our magnetic field B will be equal to B upon square root of 2, and inside we have our x unit vector and y unit vector. Now we can find out the torque. Torque is our magnetic moment and our magnetic field. We substitute both the values. We get magnetic moment was of I naught, L square and Z unit vector, and magnetic field is our B by square root of 2, and here we have x unit vector and y unit vector. And now to a simple calculation, we can write this as, we can take our B I naught L square upon square root of 2, this will be common, and inside we are left with our Z unit cross x unit plus Z unit and it's cross y unit, and Z cross x is our y unit and Z cross y is our minus x unit. So therefore we get our torque is equal to I naught L square B divided by square root of 2, and we get this as y unit minus x unit. So this is our value of the torque. And from here you can say that this torque vector is going to lie in xy plane. Torque vector lies in xy plane directed perpendicular to B. Directed perpendicular to the magnetic field, trying to rotate. Trying to rotate the loop to align its magnetic moment with B. Its magnetic moment with B. this was the first part. Now we come to the second part, in which we are supposed to find out the angle that is for a small time delta t. Part B, we have angle rotated in delta t. And from rotational dynamics, we can say our tau is equal to I multiplied by alpha, where I is the moment of inertia and our alpha is our angular acceleration. We can say using rotational dynamics, we can write our torque is equal to moment of inertia into angular acceleration. From here we can write our angular acceleration, that is our alpha, is equal to torque divided by moment of inertia, and it is given that torque is a constant and initial velocity is equal to 0. So we can say since torque is constant and initial velocity is 0, therefore we can write our theta is equal to our half alpha delta t square. We substitute value of alpha, we get this as half tau divided by moment of inertia and multiply by delta t square. And we substitute the value of tau as well as moment of inertia. Moment of inertia I is given to us, tau we just found out. So we can say that our theta will be equal to 1 by 2 and moment of inertia is our 4 by 3 ml square. Tau we calculated it as I naught L square B divided by square root of 2. Here we have minus x unit vector plus y unit vector multiplied by delta t square. We can say our L square and L square cancels out. The rest of things will be our same. So we can say our theta will be equal to, this comes as 8m root 2, 8m root 2, and numerator comes as 3 I naught b delta t square, and we have here x unit vector plus y unit vector. And this is our angle rotated. This is our angle rotated in angle rotated, and we can find out also the axis of rotation. Axis of rotation, and axis of rotation will be our perpendicular to theta, perpendicular to our theta, or basically we are going to find out, let us suppose we denote it as n unit vector along the axis, which will be equal to 1 by square root of 2, and this comes as x unit vector plus y unit vector, and this will be along the direction of magnetic field, along the direction of magnetic field. So this was the first question. And now we come to the next question. It was asked also in the year 1998, and it says that a particle of mass m and charge q is moving in the region of uniform and constant electric and magnetic field E and B are present. E and B are parallel to each other. At time t is equal to 0, the velocity v0 of the particle is perpendicular to E. Assume that the velocity is very much less than the speed of light in the vacuum. Find the velocity v of the particle at time t. You must express your answer in terms of t, q, m, the vector v0, e, b and their magnitudes v0, e and b. In this case, we are going to find out the velocity of the particle in the given parameters. So let us first of all choose the, you can say, coordinates, and because we need to find out the magnitude as well as the vector notation. So let us start with the coordinates, and so we can say that the coordinate for E coordinates, and first we choose for our electric field, and we say that it is our in z direction, magnetic field that is also in z direction, and we have a velocity v0, and that it will be our in x unit direction, because initially it is perpendicular to both E and B, okay, as that is initially perpendicular to E and B. Now we can find out easily, or rather write, you can say, equation of the motion. Equation of motion, we can say the Lorentz force on the particle will be the combination of both electric force as well as the magnetic force. The Lorentz force on the particle represented as F will be equal to the charge, and here we have electric field plus the velocity and cross product with the magnetic field. And we can also, you can say, because it is said, so we can just modify this equation and write it as m dv by dt is equal to q e plus v cross b. And let us write all these, you can say, because we need to find out the cross product. So let us divide our velocity as well as magnetic field into the components, and we can write that our velocity, suppose that is time dependent, can be written as vxt x unit vector plus vy of t y unit vector, and we have vzt z unit vector, and our b we already know is our b z unit vector. So therefore we have v cross b will be our x, y, z, and here we get our vx, vy, vz, 0, 0 and b. So this is quite simple. This will be giving us a magnetic field because the rest of the terms will be 0, only one will be present, and we get this as v, y, x unit vector minus vx and y unit vector. Therefore we substitute all these cross product as well as the vector notation of E, and we get this as m dv by dt is our q, and we have electric field in our z direction plus cross product we just found out is our vy x unit vector minus vx y unit vector. And if we separate them into component form, we can write that separate into component form, we can say that our x component will be giving us m dv by dx by dt is equal to, here we have this as q, b and vy, and then we come to the y component. Y component gives us our m dvy upon dt will be equal to minus q b vx, and we have a z component. Z component gives us of m dv by dz is equal to q multiplied by e, and we can just solve them now. And first of all we solve for z direction. Z direction means along E and B, because both electric field and magnetic field are in z direction. So we can write our dvz upon dt is equal to qe upon m. For the sake of simplicity, we can write this as dvz time dependent will be equal to qe divided by m multiplied by t plus c. And initially it is given that the component is 0, so we can say that initially we have at time t is equal to 0, vz is 0, so therefore we can say that our vz t will be equal to qe upon m multiplied by t. Now we come to the, you can say, x and y direction. X and y direction, which will be basically our circular motion, and similarly we can write that our dvx upon dt will equal omega vy, let us call the equation number 1, and we can write this as dvy upon dt is equal to minus omega, and here we have vx. Let us suppose this is our equation number 2, and here omega is our cyclotron frequency. Cyclotron frequency, which is equal to qb divided by m. So if you differentiate equation 1, this gives us a double derivative of vx upon time is equal to minus is on the other side. So we have here omega and derivative of vy divided by dt, and this gives us minus omega square and vx, and this is nothing but our acceleration and the relationship between the angular velocity as well as velocity in x direction. So from here we can say this is a simple harmonic motion. Therefore we can write that a solution vxt will be equal to a cos of omega t plus b sine of omega t. And from here we can just derivate it, and we get this as dvx upon dt is equal to minus a omega sine omega t plus b omega, and we have cos omega t, and this is equal to our omega vy. Therefore we can write that our vy of t is equal to minus a sine of omega t plus b cos of omega t. Now we are going to use initial condition, and initial condition it states that at t is equal to 0, our vx at time t is equal to 0 is our v naught. So this gives us that value of a is equal to our v naught. Similarly, we can write that our vy of 0 is equal to 0, giving us b is equal to 0. Now we can write, based on this two values a and b, we can write that our vx at time t is equal to v naught cos omega t, and the y component of velocity is equal to minus v naught sine omega t. So now we got all the values, and we can just write the velocity equation v of t is equal to v naught cos of qb m t, and our x unit vector minus v naught sine of qmb multiplied by t y unit vector, and plus qe m multiplied by t, and here we have our z unit vector. And in case we want to find the position vector, which we can also find out from this particular equation, so we can say final position vector, and first of all let us do for the initial condition. So we can assume that at t is equal to 0, our initial position vector is our 0. Now we can find out easily the first of all the x component. X component, that our x of t will be our integration of the velocity x component, and that is our integration of v naught cos of omega t dt. So this gives us that our x of t is equal to v naught upon omega, and we have sine of omega t. Similarly, we can find out our y component, and this is our y of t is equal to integration of vy of t dt. Substitute the value, we are going to get this as v naught omega, and this will be our sine is our, one second, what is our vyt? Vyt is minus v naught sine omega t. So this comes as v naught and sine comes as cos omega t. And finally, we can write our z component, z of t integration vz of t dt, and this will be our correct. So simply substitute value, this comes as qe upon 2m, and this is our t square. So we can write the position vector of r of t will be equal to v naught upon omega sine of omega t plus v naught upon omega cos of omega t, sorry, here it is x unit vector, y unit vector, plus qe upon 2m t square, and we have a z unit vector, okay, in case position vector is also asked. So we come to the next question, and the next question is said that two particles, each of mass m and charge q, are attached to two ends of a light rigid rod of length 2r. The rod is rotated at a constant angular speed about a perpendicular axis passing through its center. The ratio of magnitude of magnetic moment of the system and its angular momentum about the center of the rod is. So here we have a charge. Okay. So let us make a rod, and it is given that this rod is of mass m, sorry, particles of mass m and charge q. So we can just draw, this is one particle, charge q, mass m, this is another particle, mass m and charge q. And we have to find out, in this case, our magnetic moment and the angular momentum. And the length of the rod is given as 2r. So we have length of rod is our 2r, and constant angular speed above a perpendicular axis passing through its center. So we have this axis which passes through the center, and with constant angular velocity suppose that is omega. So we have to find out what will be the magnetic moment of the system as well as the angular momentum of the system. So first of all, let's try to find out what will be the magnetic moment. Denoted as mu. And we have, please keep in mind that the distance from the center from each charge will be known r. So indirectly this charge will be rotating about in a circle of radius r. You can say that each charge q is moving in a circle of radius r. Radius r about its center. About its center. So each is going to create a current loop. You can say, so each creates a current loop. So let us find out for single charge and then we can replicate it for both the charges. So you can say from here, for single charge q, the current due to rotation rotating charge, if represented as I, then I will be equal to over q divided by t, and the t will be our 2 pi by omega. So this comes as q omega upon 2 pi. And we can find out the area that is being swept by the charge. So you can say area swept by the charge, that is A is equal to over pi r square. So magnetic moment of one charge. Magnetic moment of one charge will be equal to mu multiplied by Ia, and our I is our q omega upon 2 pi, area is our pi r square. So this comes as half q omega r square. So we have two charges, therefore we can say for two charges, total magnetic moment and let us call that as mu t will be equal to 2 into 1 by 2 q omega r square. 2 and 2 goes away, so we get this as q omega r square. And now we are going to find out the angular momentum. Angular momentum, which is represented as capital L, and the angular momentum is about the center of the rod. Angular momentum about center of rod. Center of the rod. So the moment of inertia of one particle which is distance r from the center. Moment of inertia of one particle at a distance r we can write this as I is equal to mr square. So therefore its angular momentum L will be equal to I omega, and become this as mr square upon omega, multiplied by omega. We have two particles. Let us say L total will be equal to 2 mr square multiplied by omega. So this is our angular momentum, and we just found out our you can say magnetic moment. We have to find out the ratio. So you can say the ratio is equal to mu upon L. This is equal to 2m r square omega, and here we have q omega r square, and r square goes away, omega cancels out, so this comes as q upon 2m. So we have q upon 2m. So option number A is the correct one. Option A is correct. Now we come to our final question, year 1998, and here it was asked that two very long straight parallel wires carry steady current I and minus I respectively. The distance between the wires is d. At a certain instant of time, a point charge q is at the point equidistant from the two wires in the plane of the wire. Its instantaneous velocity v is perpendicular to this plane. The magnitude of the force due to the magnetic field acting on this charge at this instant is. So in this case, we have two straight current carrying conductors. The magnitude of the current is same, but the direction is opposite. One is I and other one is minus of I. In this case, you can say, okay, and it says that there is a point charge q equidistant from two wires. Okay. So we can draw or you can mark, let us suppose this is our point charge q equidistant from both the wires, and distance between the wire is given as d. So distance between the wire is of a capital D, small d rather. So now the point charge is at distance of d by 2, and here also our d by 2. And in this case, that everything lies in the xy plane. Only difference is that the velocity is perpendicular to this plane. Okay, so we have to keep in mind, this is important part here, that the velocity is perpendicular to this plane. So if everything is lying in xy plane, then the velocity will be, suppose, along the z-axis, perpendicular, positive z-axis for the sake of convenience. Okay. So let us call this as left side as wire 1 and right side as wire 2. and this distance is our, we already defined it, so you need not to define it again and again. So we say we have two infinitely wires, two infinitely parallel wires. We have wire 1, excuse me please, and we have wire 1 which is okay, and we can just draw a coordinate system here, and in this direction also, so this will be over x and this will be over y. So obviously the charge, for the sake of convenience, we assume that is on the, you can say, at the origin. So left side will be negative and right side will be positive. Therefore we can say y at x equal to minus d by 2, and it carries a current of I, and we have wire 2, it is x is equal to plus d by 2 and carries a current of minus I, and both lying in the xy plane. Both lie in xy plane, and like I said, the point charge lies on midway, that is at the origin. Point charge Q is located midway between the wires. That is at x equal to 0, or we can say origin. Now it is said that the velocity, charge is moving with the velocity v perpendicular to the plane. We are given charge is moving with velocity perpendicular to the plane. So let us say that is along z-axis. So we have a velocity vector, and that velocity vector is along z-axis. So this is z. So along this we have a velocity vector, and we need to find out the magnetic field at the origin. Magnetic field acting on the charge, and charge is at the origin. So we need to find out the magnetic field at the origin. So let us do the analysis by one for the wire, and we start with wire 1. So wire 1, which is at a distance of x is equal to minus d by 2 with current plus I, and we can say along y-axis, positive y-axis, upward y-axis, and we can find out that the direction of magnetic field will be along z-axis. Okay. So we can say that the magnetic field let us suppose is our B1 is along our z-axis, z unit vector for the representation. And now we come to wire 2. Wire 2, it is at a distance of plus d by 2, and it has a current minus of y, so minus of I downward along y-axis, downward y-axis, and the direction, you can say the magnetic field, in this case it is suppose B2, will be along z-axis. So both the magnetic field are along z-axis, negative z-axis rather, and we can find out that the net magnetic field let us call that as B net, will be equal to B1 plus B2. So this gives us our B net will be equal to twice of B, and we have a Z direction. Magnetic force, which we are going to find out, magnetic force, and we are given that our velocity is along z-axis. So we know that velocity, whichever v is along z-axis, and the magnetic field is along minus of z-axis. Therefore, you can say that our force will be equal to Q V cross B. So we substitute their notations, we get this as Q, and we have V Z unit plus minus, and sorry, not minus but cross Z, BZ, and we can just simplify it. This comes as QVB, and here we have Z unit vector minus of Z unit vector, that will be equal to 0. Okay. So the net force will be equal to 0. And here there is no need to write 2 because we are only interested in the magnitude as well as direction. Even if you put it, it's not going to solve any purpose. You can just write it here 2 and here 2, ultimately answer will be coming as 0. So from here we can say, even though B is non-zero, you can say force is equal to 0. Force is 0. This is because the velocity and magnetic field are along the same axis, or they are parallel. So these were the questions that was asked in the year 1998. This completes all the questions. Thank you. forgot to mark the answer. 1 second. Yeah, it has to be 0. So option D is correct. Option D is correct. Now finally all the questions are done. Thank you.